Okay, thank you. Y ahora cómo quito esto. Ah, yeah. Hi, sorry for, I had a problem with my internet or the browser, or I have no idea what happened. Okay, with an emoji, tell me how are you doing today? Hi, Beverly. I got actually a little bit nervous about not being able to get the stream done, but now everything's fine. Okay, let's start the stream. Thank you for being here. Okay, don't forget to follow us on social media. This is what the stream is going to be about. We are going to talk about classification of matter, solutions, and mixtures, and then we're going to focus on homogeneous mixtures. We're also going to do some calculations to get molarity and mole fraction. Okay, classification of matter. I'm sure you know this since, I don't know, a long time ago. This is easy, an intro. So matter, we can say that matter is anything that has mass and occupies some space. And we can classify matter into things: pure substances, and mixtures. And mixtures is actually two or more pure substances. Pure substances are things that have the same composition throughout, like any element of the periodic table, or like compounds, which, as you know, it's two or more elements bound together chemically. And mixtures, we have homogeneous and heterogeneous mixtures. Okay, I don't think you need the vocab, but here I have it anyway. The definition of everything that I mentioned for the classification of matter. So if you need to review it later, I am going to share the slides for the replay. Okay. Any questions about any of these vocab words? Okay, moving on. Okay, so a pure substance would be if you imagine that you're going to take a piece of a sample, and if it's an element, for example, copper wire, you're going to have the same composition throughout. It doesn't matter which part of the copper wire you take as a sample, it will all be uniform, and it will all be copper atoms. Or in a compound, for example, if you have a beaker full of water, but pure water, distilled water, not with anything dissolved in it, it doesn't matter in which part of the beaker you take a drop of water, it will always be H2O. So those are models for pure substances. Now in mixtures, you have homogeneous mixture. If you get a chunk of a mixture in one section, it could be different composition, but a homogeneous mixture, it would be evenly distributed, versus heterogeneous mixtures like concrete or a salad, for simple terms, it would be unevenly distributed, or you can think of it like a chocolate chip cookie. Any questions with these models? Yes, Pablo, thank you. I made it back. Thank you. Any questions about these models? Okay, moving on. Now, homogeneous mixtures are also called solutions. That's a synonym for homogeneous mixtures. So solutions could be gases, liquids, or solids. And in chemistry, the aqueous solutions are very important in chemistry because many reactions occur in water. Okay, the parts of a solution are solute and solvent. Solute is the one that is being dissolved, and usually the one with the smaller amount. And solvent would be the dissolving medium. For example, if you're adding salt to water, salt will be considered the solute, and the water would be considered the solvent. On what scale does it have to be evenly distributed? Okay, Beverly, great answer. It doesn't really matter the scale. For example, usually you consider the one in the lesser quantity to be the solute and the one with a greater quantity to be the solvent. But it doesn't matter the scale. It could be any scale. It could be, for example, seawater will have very few amount of salt considered with a lot of water of the ocean, and it will still be considered an homogeneous mixture. Great question. Did I answer your question, Beverly? Yes. So about homogeneous mixtures, correct. In homogeneous mixtures, it doesn't matter if the ratio of the substance being dissolved is big or small, as long as they're evenly distributed. For example, okay, at an atomic level, it's actually, you're going to have different elements or compounds mixed physically. So they're physically distributed. They're not chemically bonded. So the bond is not a chemical bond. So no, it won't be at an atomic level, the bonding. Okay. Okay, so here we have on this chart, we have several examples of solutions. So the state of the solution is on the first column. And then we have the solute, the solvent, and examples. So for example, air, we have a mixture of different gases. We have oxygen, nitrogen, carbon dioxide, water vapor. So they're all gases dissolved in gases. In air, for example, the solvent would be considered nitrogen because that's the gas that there's most of. And the other gases are going to be considered the solid. Or for example, we can have, for example, in smoke, we have small particles of dust dissolved in the air, and that would be considered a gas and solid solution. We have a lot of liquid solutions, for example, antifreeze or vinegar. Vinegar is acetic acid dissolved in water. We can have liquid and solid solutions. For example, as I mentioned, seawater would be an example of this. We can have a solid in solid, for example, all the alloys. Remember that alloys are mixtures of metals. So you melt the two metals and then solidify them back again. So it would be a solid in a solid. And the solid in a gas would be, for example, a hydrogen in palladium. This one is just as a semiconductor, and the hydrogen helps with this conductivity. Questions about these examples? Okay, we're going to move on. Okay, so since we have variable compositions for solutions, we need to specify these amounts to decide, for example, the distribution that Beverly was talking about. So there's two ways to measure or to explain to other people what this distribution is all about. The most common in chemistry are molarity and mole fraction. There are others like mass percent or molality or normality, but we're just going to focus on these two since they're the most common. And you're only going to be asked about those two on the AP exam. So molarity is moles of solute, so the one that is in the lesser amount, over liters of solution. And solution is the whole thing. For example, if we are going to think of molarity of seawater, the moles are going to relate to the salt, and the liters are going to relate to the water plus the salt, with the salt in it. So the liters of the whole solution. And the units or the symbol for molarity is capital M, and it's mole over liter. Any questions about molarity? Okay, we're going to move on with the other one. We also have mole fraction of any of the components of the solution. We're going to do a fraction of the moles of A, or whatever they're asking, over total moles of solution. So if, for example, if we only had two things on the solution, then on the numerator, we're going to have the one that they're asking us. And on the denominator, we're going to have both things that make the solution. Okay. Any questions up to here? Okay, moving on. Okay, we're going to do some examples of molarity. I placed here on the top just the formula to remind us. So if they ask us, for example, what is the molarity of 30 grams of sodium hydroxide in 0.250 liters of solution? I recommend you to sorry. I recommend you to organize your work. So if you organize your work, teachers love this, by the way. So do this, and you will for sure make your chemistry teacher happy, and you will get more points in the AP exam. So if you organize your work, you're going to place the given which is just copying the data that you're given. The required is molarity of solution. So then we need to think about what can we do with this. If we have that molarity is moles of solute, from this data, from where can we get from which of these values can we get moles? From the grams, can we switch grams to moles? Or can we switch liters to moles? Okay, we are going to use grams to change it into moles. And if we remember from the beginning of the school year, we use the molar mass to change grams to moles. So you get the molar mass of the atoms of sodium, oxygen, and hydrogen. You add them up, and it will give you 40.01 grams of sodium hydroxide, and that will represent that 1 mole. So if you place it as using this process of dimensional analysis, you can cancel grams of sodium hydroxide, and then you now have moles of sodium hydroxide on the numerator, which that's what you want. But now, what do you have to do to finish this problem? Okay, what you have to do to finish this problem is divide by liters of solution, which in this case is 0.50 liters of solution. You also have to notice the significant figures in the data. And then in your required, you will need three significant figures, since you use the least amount of the given. So then your answer would be 3.00 molarity. Just a reminder of how to round with significant figures. This would be what you will get on the calculator. So if you need 3 sig figs, you're going to stop it here, but use the next number to round up or down. In this case, you round up, and that's why you end up with 3.00. Don't forget to place the unit and the label and to box your final answer. Your chemistry teacher will be very happy with it. Okay, any questions about this problem? Okay, let's move on. Another example of molarity, but now we're going to use molarity as a conversion factor. For example, if they ask you, how many grams of potassium chloride would you need to weigh out to prepare a solution, 2.50 liters of solution of a 2 molarity KCl solution. So what you're going to do is you're going to, again, list the given and the required. And then you're going to start with the liters. And then you're going to switch the 2 capital M, the 2 molarity, to its components, which are 2 moles per liter. So by doing this, now I can cancel liters of KCl. And in this step, you already will have moles of KCl. So by using again the molar mass from the values of the periodic table, you can now cancel moles of KCl, and you will end up with the unit that you want, which is grams. Again, you need to be aware of the sig figs and report your answer with the proper significant figures. Box your final answer, and you're done. Any questions? Okay. So now I am going to prepare a solution. We are going to use this example, 37.3 grams of KCl. We're going to use that to prepare a 2 molar solution. Okay, so I'm going to, I am going to unfocus the screen. Give me a second. Okay, so I am going to try this. I'm going to place some books to gain some height. Okay, we are going to use this flask. This is called a volumetric flask. This is at 250 milliliters because remember that we needed 2.250 liters of solution. So to prepare a solution, you use a volumetric flask of the appropriate volume. Yes, a real example, Camila. Thank you. Okay, then you add a little bit of water, not too much. Just a little bit to dissolve. Then you're going to use a weighing boat. I do this with, I usually use wax paper. Filter paper also works. And I don't know if you know how to fold this. It's very, very simple. I am going to show you. With a piece of paper, you're just going to make these folds. You make the folds. And then on every corner, you fix it for every corner. And I also like to, this is like origami. You make a fold again, and then you will have a weighing boat, okay? So you use your weighing boat, and I didn't brought a scale, but suppose that I'm using salt from my kitchen, regular salt, but suppose that it's the KCl from the example above. Suppose that I weighed already the 37.3 grams. Of course, you're going to be using a scale for this. Then I love these kinds of boats because then if you unwrap a corner, you can pour your sample really easily. You know how I make this corner? Now you place the solid sample carefully. Make sure to add all of it. If anything gets trapped here, like it happened to me here, don't worry. You can use one of these bottles. Yes, you can also use a funnel, Pablo. Yes, that's a great idea. You can use these. I love these water bottles. These are very, very useful. By doing this, you're moving all of the solid to the bottom. Then, just with a little bit of water, you place the lid and you dissolve. You make sure you dissolve everything. Sometimes you will need to heat it up a little bit, depending on the substance that you're being dissolved. Sometimes, if you heat it up a little bit, it will dissolve faster. Okay, so you dissolve. So this is the shape of this volumetric flask. Helps us dissolve much, much easier. So I think it's pretty dissolved by now. We don't have any solid on the bottom, so we may continue. You remove the lid, and now you're going to add water. Of course, you need to use distilled water on the solutions. You don't want tap water because then you're going to get other minerals from your tap water in the solution. So you need to use distilled water. Okay, then you're going to add water and make sure your eyesight is at the level of the mark. Don't never ever do this because then you're not going to be accurate. So if you're on your table, make sure you lower your eyesight to the mark. So you can add water. You can add water, and when you're close to the mark or to the neck of the flask, you want to slow down a bit. Okay, here you have to be careful. And I would use again my water bottle because if I use the beaker, I will overpass the mark. So you can use and if you don't have a lot of experience with this, you can do the very last bit. You can use a dropper for the last section. So you lower your eyesight, and with a dropper, you carefully add water to the mark. You're done. So now you have the grams needed to get the molarity, the moles needed, and you have the total liters of solution. So one thing to explain here is that you never add, for example, here, if it's a 250 liter solution, you never add the 250 liter of water because you will surpass the level. The 250 milliliters is the whole solution. Then you can place the lid back again and make sure you distribute it evenly. You're done. Now you're ready to use the solution in any lab session that you need. Any questions? Okay, I'm going to move my lab station. Okay, and I am going to share my screen again. Okay, so what we did with the volumetric flask was prepare the 2 molarity KCl solution in 250 milliliters. Any questions? Okay, we're going to move on. Okay, so now we're going to explain the mole fraction concept. Mole fraction, the symbol is a lowercase Greek letter chi, and it refers to the ratio of the number of moles of a given component to the total number of moles in the solution. So that's our formula. Let's do an example. So if this was the problem, a mixture of gases that contains 4.46 moles of neon, 0.74 moles of argon, and 2.15 moles of xenon, it says to calculate the mole fraction of neon in the mixture. So what's the first thing that you need to do so that your chemistry teachers love you? What should you do first? Okay, what you do first is organize your data. So you organize your data and you list the given and the required. And it will be a nice idea to start thinking about the significant figures. Okay, then you place your formula and then you substitute. And let's think here about the significant figures. We have 3 significant figures, 3 on the bottom, 2 and 3. But what do we do with significant figures when we add numbers? What do we have to take in account? Do we remember from the essentials in the beginning of the year? Okay, yes, Ryung, you use the least, but you use the least number of decimal places. So here, the least number of decimal places would be two decimal places. So if we do this addition, we will get as an answer 7.35 with 2 decimal places. So now the 7.35 on the denominator will have 3 significant figures. Now, when we do the division of 3 significant figures on the numerator and on the denominator, we will need 3 significant figures on our answer. So that's what we need to do. And we will get 3 significant figures. Remember that this 0 doesn't count. So 1, 2, 3 significant figures, and that would be the answer for this problem. Don't forget, this number doesn't have a unit because moles and moles get canceled. So I just placed mole fractions of neon in the mixture as a label, but actually this number is unitless. Questions? Okay, we're going to move on. Okay, now we're going to do another example where we do both molarity and mole fraction. So this is the problem. A solution is prepared by mixing 1 gram of ethanol with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity and mole fraction of ethanol in the solution. So again, what do we do first? What is the first step? Remember, we want the teacher to have a neat. Correct. We are going to list the givens. Excellent. We're going to do the givens and the required because we need to learn how to organize our work. We need to make it easy for anybody else to read our work and read it neatly and nicely. So yes, we list the givens. There's no need for you to place the significant figures. I just did it here for teaching purposes, but you can omit the suffix in the given. And the required in this case is both the molarity and mole fraction. Okay, let's do the molarity first. What is the formula for molarity? Okay, the formula for molarity is moles of solute over liters of solution. So if they're telling us to calculate the molarity of ethanol, then ethanol is our solute. Okay, what information do we have about ethanol? In your list of givens, we have the 1 gram of ethanol, right? So we can start with that. How can we change grams of ethanol to moles of ethanol? What do we need to do? Okay, what we need to do is to change it to moles using the molar mass. Remember that the molar mass, we get the values from the periodic table. So we get the molar mass from the periodic table, and if you don't remember how to do this, you get the molar mass of carbon, which is 12.01 multiplied times 2, then get the one of hydrogen, which is 1.01 multiplied times 6, since we have 6 atoms of hydrogen, and then get the one of oxygen and multiply it, and well, it's only 1 atom, so 16, and then you add them all up and you will get this value. So by having this conversion factor, we're canceling grams and we have moles. Okay, we have moles already. Now, what do we need? From where do we get the liters of solution? Which volume should we use? The volume that we get in 100 grams of water, or the final volume? Correct, correct. Excellent, Camila and Young. We use the final volume. So we are going to use the 101 milliliters, but in the formula, we need liters. So how do we change milliliters to liters? Do we remember the conversion factor of milliliters to liters? The prefix milliliter should help you remember. Exactly, or another way to say it is 1,000 milliliters, it equals 1 liter. So once we set up the problem this way, we already cancel grams, we already cancel moles. I'm sorry, we didn't cancel moles. We already canceled grams, and we already canceled milliliters. So our units are going to be moles per liter, which is precisely what we needed for molarity. So we're done. We're done. We use our calculator and get the answer. Any questions on how to solve this problem? The definition of molarity is moles of solute over liters of solution. Okay? Okay, excellent. So now we need to move on to now calculate the mole fraction. Okay, so the mole fraction, we are going to use this formula, and now we need to get moles of the ethanol over moles of the ethanol plus the water. So again, we use the grams of the ethanol and the molar mass to change to moles, and then we use the 100 grams of water by the molarity of water to get the moles of water. And then we just place it on the fraction to get the mole fraction. Okay, so we are going to get, using 3 sig figs, this is our answer. And remember that this is a unitless number because we're canceling moles. Any questions? Okay, we're moving on. So now, another example where they ask us to calculate molarity and mole fraction. And here they're giving us density. It's a little bit different data, but we can figure it out. So in this case, a solution is prepared by mixing 25 milliliters of pentane, and they give us the density of pentane in units of grams per cubic centimeter, with 45 milliliters of hexane. Okay, here we are going to assume the lesser amount, pentane, to be the solute, and the greater amount, hexane, to be the solvent. And then it gives us another note. Assume that the volumes are unmixing. So the total volume would be the addition of 25 plus 45. They're asking us again to calculate molarity and mole fraction. So we list our givens, we write the required, and then we can start figuring this out. Okay, how? Remember that the molarity is moles of solute over liters of solution. Which data could we use to get moles of solute, in this case, pentane? How can we use this data to get moles of pentane? Okay, we can start with the milliliters that they gave us, and then we can use the density. If we remember, grams per cubic centimeter is the same unit as a milliliter. So we can transform the units of grams per cubic centimeter to grams per milliliter. By doing this, I am canceling milliliters of pentane, and now I have grams of pentane. Now we can do as we did on the previous problems, where the grams can be changed to moles using the molar mass. And then we can divide by the total volume of the solution. In this case, the addition of 25 and 45. So 70 milliliters. And lastly, we change the units of milliliters to liters. So now if we check our units that we didn't cancel, well, noticing that we didn't cancel moles and we didn't cancel liters. We cancel milliliters, we cancel grams, we kept moles, we cancel milliliters from here, and we got liter on the denominator. So we're done with the setup. We use the calculator, and that's our answer. Notice how on the given, we have two significant figures in all our given. So that's why we must have two significant figures in our answer. Any questions so far? Okay, moving on. So now we have to calculate the mole fraction. So we do the same thing. We get the moles of pentane and the moles of hexane, and then we place them in the fraction. So the moles of pentane in both of the substances, we use the same process to get 2 moles. We place the milliliters, we multiply times the density, because by doing this, we're canceling milliliters. And then we use the molar mass to cancel grams and get 2 moles. We do the same process for hexane, and now we have the moles of both substances. We place it on the fraction. We are aware of the sig figs, and that's our answer. Any questions so far? Okay. In a ratio, if we are going to, in a scale from 1 to 5, how do you feel with these concepts of molarity and mole fraction? 1 meaning I didn't get this at all. And 5 meaning I'm an expert. I can teach it to my peers. What would be your score from 1 to 5? Do you feel confident with these concepts? Okay, Camila, what do you think you struggle the most? Or you just need to review on your own? Okay, I'm going to, yes, practice. It's always a very good choice. I'm sure you have a lot of problems on your chemistry book, and most of the books have answers on the back of the, for some of the problems. So use these to practice. I will leave these slides on the content of the replay. And you will do better. You'll do fine. Okay. Anybody else? What about the rest of you? How would you score yourself on a level from 1 to 5? Okay. It's okay. Okay, so there you have, the slides are going to be there. That's all from my part. Thank you for your attention. Bye-bye. Nice having you on this stream. Bye-bye. Good night.